Welcome, this is lecture 59. So, in this lecture and in the next, we will discuss Castelnuovo Mumford regularity, which is another invariant about numerical invariant of a module that we see from a free resolution. There are other ways of seeing it. The original definitions were different. This is what we are using as an equivalent definition. Okay, so we'll again work with polynomial rings graded with degree of xi equals 1, and M is a finitely generated graded R module. Okay. Then by Hilbert-Szysgy theorem, okay, its projective dimension is finite. M has a finite free resolution. Okay, and we define, and then we also know what is called graded Betti numbers. Okay, so these are the graded Betti numbers. Okay, the number of copies of Rj that appears in position I of the free resolution. Okay. The Castelnuovo Mumford regularity of M is, so which we denote by reg M. Okay, this is the maximum of the differences j minus I such that beta I j of M is not 0. Okay, and because it has a finite free resolution, eventually for large enough, for I greater than n, for every j this is 0, and in any case for a given I there is only finitely many non-zero such. There are only finitely many j where this is non-zero, so this maximum is indeed a maximum. Okay, so we can look at a Macaulay example. So we take a polynomial in 3 variables x, y, z. Then we ask for the ideal generated by x square and y cube, and then here is we ask for the resolution of I. Then we ask for what is called the Betti table of I. Okay. So resolution of I is this is a, if you notice this is a, one can show that this is a regular sequence. Okay. X square is a non-zero divisor, and R modulo x squared y cube will be a non-zero divisor. Okay. So this is a Koszul complex. Okay. So what information do we need, do we see from here? So the one here just means that it is a quotient of a rank 1 free module. So when we ask for resolution, it resolves R mod I, not I. Okay. Now here, this one here, this one here means that in homological, in the position 1 of the free resolution, in degree 2 there is a basis element, and here it says degree 3 there is a basis element. Okay. So that just corresponds to the x squared and y cube, and then it says it is a relation in degree, so their relation is in degree 5, okay, which is y cube times the basis element here minus x squared times the basis element here. So that relation will be in degree 5, and this is what it says. And if you notice this has already taken the j minus I difference. Okay, remember in position I plus I, column I, row index j, it is already beta I plus j. So in other words, regularity is just the index of this bottom row. Okay, so one can look at the Betti table of a module, then immediately tell what the regularity is. Okay, regularity here is 3. That's what we were asking here. So the difference is so here when we ask for regularity of I, see I and R mod I are different modules. For resolution, if you ask for I, it actually computes for R mod I. But we ask for regularity of I, it computes the regularity of I, not the regularity of R mod I. And we will see that they are little different. Okay? So we have to actually ask for regularity of the co-kernel of gens of I, which is the same thing as saying R mod I. Okay? So, and it is 3, which we see from this row. This. Now, suppose we want the regularity of the module, which is actually I. So, we ask for a resolution of the image of the generators of I. Okay. If you ask for a resolution of I, it will just take the co-kernel R mod I. Now, we actually have to ask for that map. So, then we just get a map from R1 to R2, and this is the Betti table. Okay. So, the difference between this Betti table and the other Betti table is, here there is an I, there is an 1 here corresponding to R. There's one more difference, the row indexes have changed, because the row index 1 here in this column is degree 2, but in order to get that in degree, the row index will be 2. So, this one's regularity will be 4. Okay. Regularity of the ideal is 4, regularity of the quotient is 3. Okay. And, I mean, it is indeed true. Let's y. So, here suppose we have a free resolution of R mod I. Then just chop off this part, we get a free resolution of I. And conversely, if you have a minimal resolution of I, just put an R in here and then we get a free resolution of R mod I. So, if you look at the graded Betti numbers, beta ij of R mod I is beta I minus 1 j of I. So, hence the projective dimension of I would be 1 less than the projective dimension of R mod I, because the resolution has gotten shorter. However, the regularity would be 1 more. That's because we are subtracting j minus I here. The same quantity here would be subtracted as j minus I minus 1. Okay, so it would the regularity would be 1 more, and that's all that we have observed here. So we have to keep this in mind that unlike resolution, if you give resolution of an ideal, it computes the resolution of the quotient. But you ask for the regularity of the ideal, it actually computes the regularity of the ideal. We can compute the Hilbert function from the free resolution. Okay. In fact, we can determine the Hilbert polynomial. Well, Hilbert function is okay. And then so let's. This is not very difficult to see. So what is it that we have? We have an exact. So we have an exact sequence. 0 to some fn. I'm not saying that these are non-zero free modules, but we just know that it doesn't go beyond fn, so we just call it, just stop there. Okay, so this could be 0, it doesn't matter. f1 to f0 to m to 0. So we have a free resolution, and then we put this augment with this module, okay, with this so exact sequence of graded R modules, okay, and degree preserving maps. Okay, so this is what we have from a free resolution, and okay, so we are not going to use explicitly now that these are. I mean, we don't need to use it. This is a minimal free resolution. But just to simplify the calculation, get a nicer expression, or at least get some workable expression, we will assume that it's minimal free resolution. So we can take this to a minimal free resolution. Okay, I mean, there's just set beta ij, remember beta ij is 0 if I is bigger than the projective dimension of n. So we can still treat it as okay. So then from here, because it's degree preserving maps, we can break this whole complex into its degree. Okay. So in degree some d, in degree d, so the rank of this module, so in each degree this would be a complex, this would be an exact sequence of k vector spaces, finite dimensional k vector spaces. So for each d in z okay, degree, okay, the exact sequence, the above exact sequence gives an exact sequence of finite dimensional vector spaces over K. Okay. So then we can write down the rank of M in degree D. Yeah. Therefore, rank of M, rank over K of MD is, well, this would be the alternating sum. It would rank of this in degree D minus the rank of this plus the rank of this minus the rank of this and so on. Okay. Minus 1 to the I rank over K of Fi in degree D, and this goes from so the okay, in other words, the things at 0, 1, 0, 2, 4, etc. all get positive sign. The other ones are subtracted, and this alternating sum will give the rank of MD. Okay, so just write down an exact sequence of vector spaces and convince yourself that such an alternating sum, this is such a thing is true. This is just, I mean, this comes down to rank nullity theorem. I mean, it's just many applications of the rank nullity theorem. Okay. So then, so we get this thing. So now we can just sum up to construct, multiply by some dummy variable t, powers of a dummy variable t, and then sum it up to construct the Hilbert series. Okay. So what does that tell us? It gives us hm of t. Okay, so we are just multiplying this by t to the d and then summing up. Sorry, this is not d, this is n. Okay. I goes from 0 to n minus 1 to the I. Rank of, so again, we multiply this by t, but then when we sum up, we sum for each I. We're changing some order of addition and sum, but this is, we're not worried about some convergence, so it's just a formal sum. So this is h of fi. Okay, so this is, there is the Hilbert series also has this alternating sum property, so we get like this. But this can be described, so fi has beta ij copies of r minus j, and r minus, so fi is direct sum of r minus j appearing beta ij many times, and this is j in z, but only finitely many of these are non-zero. Okay, so we can, okay, so j in some finite set, but integers. Okay, so this is what we have. So therefore, hf is sum, okay, over j in z, h of r minus j, this t, times beta I j. Okay, each copy will contribute 1 to this thing. But what is this number? So let me just rewrite it like this: beta I j times, the generator here is in degree j, and rest of it looks like the polynomial ring. So it's going to be t to the j divided by O divided by 1 minus t to the n. Remember, the polynomial ring in n variables, the Hilbert series looks like 1 over 1 minus t to the n. So we write j equals z, but only finitely many will show up. Okay. So therefore, putting this together, we see that HMT is I goes from 0 to n, j in z, minus 1 to the I, j in z, beta ij, t to the j over 1 minus t to the n, 1 minus t, the quantity to the n. Okay. So this is going to be some polynomial in t, some Laurent series in t, depend what j's are. If j is negative, it may not be a polynomial. So this is going to be some Laurent polynomial in t divided by 1 minus t to the n. Okay, just put this common factor. Okay, so this is just a way to get, but it can be determined by the beta ij itself. So in some sense, the free resolution encodes more. It's a refinement of the Hilbert function or Hilbert series. Okay. Hilbert function, Hilbert series encode the same information. It is just one is written as a function, the other one is written as a generating function for that thing. Okay. So this is this. So where does regularity come into picture? So it's not okay. So proposition. For all d greater than or equal to regularity of m plus 1, the rank of m in degree d is it's given by the Hilbert polynomial. Okay, remember this is the Hilbert polynomial. You do not need, it is actually given by the polynomial. So the difference between the Hilbert function and Hilbert polynomial will occur before it attains the regularity. After the regularity, it is all before or at. After it attains regularity, it will be given by the polynomial. Okay? So this is so this is one place where so this is one place where if you knew regularity, then we know from there onwards, or regularity plus 1 onwards, what the Hilbert function is, just by looking at the Hilbert polynomial. Okay? So we'll prove this. So it goes back to looking at this expression. Okay. So let d be greater than or equal to regularity of m plus 1. Okay. Then rank of m in degree d, okay. This is, so here we wrote the Hilbert series, but we can go back to this expression. We can go back to this expression and put this inside there to rewrite this. So rank of this is from 0 to n minus 1 to the n. Okay. Now we are worried about fi. So there's going to be a j in z, beta ij. Okay. Rank of r minus j in degree d. Rank over k. So notice that we want minus 1 to the rank of, from here, we want rank of fi in degree d, but fi in degree d is this module in degree d, so the ranks just add up. And I mean, this is just a direct sum, that's also a direct sum. Okay, so they just beta ij times the rank of this in degree d. That's all that we have written here. Okay. Now, what is this number? Okay. So, d is Okay, so we need to determine that number. Okay, so what is rank of R in degree D? Okay, this is, so there are n variables, so it's going to be n minus 1 plus D choose n minus 1. Okay, binomial, so this one can prove by induction. So n minus choose D choose n minus 1. And so if you think about this function, so let's write this as a function in D. Okay, so we are saying that this rank can be written as a polynomial in D. Okay, so let's write this as a function in D. So it is going to be n plus D minus 1. Maybe. So this is n plus D minus 1, n plus D minus 2, all the way up to D plus 1, divided by n minus 1 factorial. Remember, this is that number factorial divided by this factorial times D factorial, and we have just removed the D factorial from here. Okay. Now, if you think of it as a function in D, so this is a polynomial in D, polynomial of degree, so there are n minus 1 terms here, okay. N minus 1 in D, polynomial of degree n minus 1 in D, okay, and has n minus 1 zeros. Okay. D equals minus 1. So just think of it as a polynomial in D. That polynomial has these many zeros. D equals minus 1, D equals minus 2, all the way up to minus of n minus 1. That's what is expressed. If you plug in any of those values of D, we would get 0. Okay. So this is a polynomial which has these zeros. So now let's use this for our thing. Okay. So now our assumption is that D is greater than regularity of M, okay, which implies that D is greater than J minus I for all Ij such that beta Ij is not 0. Which in particular implies that the maximum value of I is n. D is greater than J minus n for all J such that beta Ij is not 0. Okay. I mean J minus I is bigger than J minus n. So we get this condition. Okay. So now what does that say? So now let's go back to, okay, so this is what we have. So we know this. Okay, this is the rank of RD. What is the rank in degree D of R minus J? Rank of over K of R minus J in degree D is so this is the same thing as degree D minus J. Okay, so we can put that in this expression, D minus J, n plus D minus J minus 1 all the way up to D minus 1 plus D minus J plus 1 divided by n factorial. Okay. And this is, okay, so this value is given by a polynomial for everything. Okay, so the zeros of this are J minus 1. Okay, so the zeros of this polynomial are J minus 1, J minus 2, all the way up to J minus n plus 1. Okay. So this is given by a polynomial. So rank of K in R minus J in degree rank over k of r minus j in degree d is given by a polynomial for all d bigger than j minus n. That is because if it is less than j, I mean if it is like j minus n plus 1, the rank of this is 0, so is the value of that polynomial. Okay. So this polynomial is such that from, let's go back to the polynomial for r, this polynomial is such that for degree 0 onwards, it has non-zero value and agrees with that rank. But from minus 1 to minus n minus 1, it has value 0, and therefore again it agrees with the values of this. I mean this is 0, so is this, in this range. So in fact for the polynomial ring, the Hilbert polynomial agrees with the Hilbert function from my polynomial ring in n minus 1 variables. The polynomial Hilbert series agrees with the Hilbert polynomial agrees with the Hilbert series from minus n plus 1 onwards, not from 0. It is just that the first part is, it's not very relevant. They are both the Hilbert function and the polynomial take value 0. Okay, so so this is the point. Even though this module is generated in degree j, and its Hilbert function is 0 between when d is less than j, it is still given by this polynomial. Okay. So therefore, this implies that, so now this is just a, therefore for all d greater than, okay, so remember we got this condition because of d greater than m. Therefore, for all d greater than regularity of m, rank k of m in degree d, rank over k of is given by a polynomial in d. Okay. But if there is a polynomial that gives it for every value greater than this, then it must be equal to the Hilbert polynomial. Okay. This must equal the Hilbert polynomial. Otherwise, when you can't have two distinct polynomials that agree with infinitely many that agree with each other for all, I mean two such polynomials with values in z, which polynomials like this, which would agree for every integer sufficiently large. That is not possible. So therefore, if it agrees like this, I mean if some polynomial shows this behavior, then it must be the Hilbert polynomial. So that's the end of this proof. Okay. So this is one application of regularity, and this application goes back to Castelnuovo and in modern thing to Mumford. I mean who redid it in modern, I think, modern language. I mean, but it is not written in terms of Hilbert. It is not written in terms of free resolutions. That translation came later. And so, which is why this invariant is called Castelnuovo Mumford regularity. Okay. So this is the end of this lecture, and in the next lecture, which is the final lecture in this course, we will use this to look at a simple geometry problem, which is stated without reference to any of these things. Okay. So this is the end of this lecture.